One of the basic concepts of computer programming is that of a variable. We've been using variables already, but now I think it's time to discuss some of the fundamentals of this concept. A variable in a computer program is somewhat, but certainly not completely different from a variable in algebra. In a computer program, a variable refers to a storage location that holds a value. Therefore, at any point in a program, a variable refers to the value currently stored in the given location. Most programming languages have variables of different types to refer to integers, single precision numbers, double precision numbers, and so forth. Matlab is no exception. However, Matlab differs from many, if not most, languages in that variables do not need to be declared, and every variable has the same default type, namely that of a double precision multidimensional array. Moreover, such an array is resizable. So let's look at some examples. If I type x equals 1 and then give the command whos, I see that x is a 1 by 1 array. It occupies 8 bytes. It is of class double. Now, a double precision number requires 8 bytes for storage. This is a 1 by 1 array, which means it has only one element. So you can see why a total of 8 bytes are required. Now, I said that an array is resizable. I could type x of 2 equals 3. And now x becomes an array with 1 row and 2 columns. It's now a 1 by 2 array. It now requires 16 bytes because there are 2 double precision numbers being stored. I could type x of 10 equals 4. Matlab now resizes the array to have 10 entries, still 1 row. And Matlab fills in 0 for any of the entries that have not been assigned yet. I can resize x to have 2 rows. So I just assign the second entry in the second row to have value 2. Now x is a 2 by 10 array. A 1 by 1 array is thought of as a scalar or a number. An n by 1 or a 1 by n array is usually called a vector, and an m by n array is called a matrix. We can even use 3-dimensional arrays or k-dimensional arrays for k greater than 3. So for instance, if I say I want x of 3, 3, 3 to equal 7, now x is a 3-dimensional array, and you see there the 3 slices of x as they're referred to. The first slice was the original matrix that we defined, and then a second slice turns out to be all zeros because I haven't assigned any values in that slice. And the third slice has a single non-zero. In this course, we're only going to use numbers, vectors, and matrices. Since a double array is the default type, if we want a variable of a different type, we have to create it explicitly. In this video, I'm only going to discuss numeric types, namely single, double, and various integer types. In an earlier video, I discussed briefly single precision variables. I can create a single precision variable holding the value 1 as follows. Now x is a 1 by 1 array, in other words, a scalar. The class is single, so it's a single precision number. It only requires 4 bytes to store it. Now let's consider the following calculation. Suppose I add 2 to the negative 30th to x. It appears the answer is still exactly 1. I can check that by subtracting 1 from the answer, and indeed I get exactly 0. Now let's compare this to the following calculation. By default now y is going to be double precision. If I add 2 to the negative 30th to y, I get a number that's not exactly 1. In fact, I get exactly 2 to the negative 30th, as you would in exact arithmetic. What's going on there is that the double precision number has enough precision to exactly represent 1 plus 2 to the negative 30th. On the other hand, the single precision number does not have enough precision. In fact, it only has 23 bits of binary precision. So it cannot represent 1 plus 2 to the negative 30th. That rounds down to 1. The advantages of using single precision variables are that less memory is required, and usually less computation time is required. It's usually faster, for instance, to multiply 2 single precision numbers than to multiply 2 double precision numbers. That statement, though, does depend on the processor being used, and it may not be true on all computers. The main disadvantage is a significant loss of precision. As an example, let's compute the sum of the integers from 1 to n for n equals 1,000,000. Here's the exact sum. Of course, I have a formula for this. It's n times n plus 1 divided by 2. So it's 5 times 10 to the 11th. Here's the computation in double precision, which is the default. So I set x equal to 0. For I equals 1 to n, I set x equal to x plus I. What's the result? Well, it's exactly the same as s. Here's the same computation in single precision. So I have to create a single precision variable y. And for I equals 1 to n, I replace y by y plus I. Now my answer is actually quite different from the exact value. This may not be quite as bad as it appears because what really counts is the relative precision. The relative precision is about 0.0001, which means 1/100th of 1%. I would consider that to be a relatively large error. Note that if you want to use single precision to save memory and or time, you have to be careful. If you accidentally assign a double precision value to a single precision variable, that variable will revert to double precision. So for instance, we see now that y is a single precision variable, but if at some point in my program I set y equal to 1, y becomes double precision because on the right-hand side of that assignment statement, y equals 1, that number 1 by default is a double precision value. Assigning it to the variable y causes y to become a double precision variable. Matlab has several integer types, in fact 4 signed integer types and 4 unsigned integer types. To see a list of these, let's go to the documentation maintained by the MathWorks, the company that produces Matlab. So I'm going to open a browser. I'm going to do a Google search on numeric types in Matlab. I want this first page. It describes the numeric types and gives them a list here. And you see, as I said, that there are a total of 8 different integer types. Int 8, that's an 8-bit integer. Int 16 is a 16-bit integer, and so forth. And there are also these unsigned integer types. For instance, uint 8 is an 8-bit unsigned integer. Uint 16 is a 16-bit unsigned integer, and so forth. Although I want to emphasize this, let's take a look at these utility functions that are listed on this same web page. Matlab provides a function isInteger that allows you to test if a variable is an integer or not. IsFloat tests whether a variable is floating point. IsNumeric would test whether it's integer or floating point, and so forth. So you might find these utility functions useful at some point. Going back to the integer types in Matlab, these types can be used to save on memory, but I want to warn you that they should be used with care because of the limited range. For instance, you might choose an unsigned 8-bit integer because you want to save as much storage as possible, but the largest number that you can represent using an unsigned 8-bit integer would be 2 to the 8th minus 1, which is 255. A common mistake that programmers make is to think, well, I have this application in mind. 255 is certainly larger than any integer I'm going to encounter in this application, and so I'll take advantage of this memory saving device. But at some time later, the program expands in its range of application, larger integers are encountered, and the program fails for a mysterious reason. So I just want to warn you again, if you do take advantage of these types to save on memory, be careful of the limited range that they represent. In this class, I'll generally use the default numeric type, which is double precision. A key property of a variable is its scope, which describes which programs can access the variable. A variable can be local or global. The default and usually recommended scope is local. Variables in the Matlab workspace, the variables you see listed when you type whos in the Matlab command window, can be accessed in the command window or in any script called from the command window. However, such a variable cannot be accessed in a function called from the command window unless that variable is passed as an input. A variable created in a function, that is a function m file, is visible only inside of that function. It's independent of any variable of the same name in the main workspace or in another function. I'm going to create a couple of m files as examples. This first m file is going to be a script. I'm going to set n equal to 100, s equal to 0, then for I equals 1 up to n, I'll set s to s plus I, and that's all. So this script is just summing the integers from 1 to 100. I'll save this and I will call it tsum. Now suppose I'm in the command window. I have no variables declared at this point. Suppose that I'm doing some work and for some reason I has the value 13, and then I need to call tsum. I now have 2 additional variables, the variable I, the variable n, the variable s. S, of course, is what I wanted to compute in that script. N is 100 as I set it to be. But the important thing for this example is that the value of I has changed. I was 13 before I called the script. I is 100 now. That sort of a side effect is often undesirable. Let's create a second script. This is going to be a function. It's going to be s equal tsum1 of n. And I assume that n is input. I'm just going to set s equal to 0, and for I equals 1 to n, s equals s plus I, end. Save it, As I said, that's going to be called tsum1, which you notice is the default name chosen by Matlab because that's what I named the function in the function line. So I save it. And again, I'm doing some work and I set I equal to 13. And then I say s equals tsum1 of 100. Now s is 5050 as before. But now I still has the value 13. It did not get changed or overwritten when the function tsum was called. In this example, due to the concept of local variables, I actually have two variables named I. One is in the Matlab workspace, and one is a local variable in the function tsum1. Those variables are completely independent of each other. Changing the value of one does not change the value of the other. Most of the time when we write programs, we want to take advantage of local variables to avoid unpredictable side effects. Matlab does allow global variables. A variable is global if it's visible across different functions. I don't recommend using global variables usually, and I'm not going to use them in this course. But if you're interested, I recommend using this Matlab documentation. I do a Google search on global variables in Matlab. This page will explain how to use global variables. Once again, I don't generally recommend this, and I'm not going to use global variables in this course. I do recommend writing most of your Matlab programs as function M files, especially those programs that you plan to use more than once.